Oh, okay, we're good. Hi, everybody. My name is Kevin O'Brien, and this is the YR webinar series. Today, we are joined by Professor Jonty Rougier, or Jonty, if that's okay. Yep. And you're going to be talking about estimating volumes for, sorry, just off the side. Sorry, I'll let you introduce yourself. Sorry, I forgot that the name's just cropped. So first off, let me thank our sponsors, Jumping Rivers. They're a consultancy based in Newcastle in the UK, and they are a data science consultancy and training company, and they've been great sponsors and supporters of our user groups and events like Saturdays over the past few years. Also, we are delighted to be joined by our users all over the world, and we noticed that we get great support from the likes of the Barcelona R user group, the Lille R user group, and many more around Europe. And also, sorry, some of the Our Ladies groups like Abuja and Tunisia, they should be joining us tonight. If you're watching us in the chat, or watching us, tell us in the chat where you're from, because we always get a great kick out of, a great enjoyment out of seeing where the R community is spread around the world and how far and wide the R community is. And if you have any questions at the end, or just ask them in the chat, and we'll ask them at the end of the presentation. So I'll hand over there to Jonty, and we'll get cracking there. I'll go stop my screen, and you can start sharing there. If you got
okay.
It.
Mm-hmm. Right, good evening, everyone. Well, it's evening where I am anyhow. Kevin, does that work okay?
Yep, perfect.
Great. So it's a pleasure to be talking to you from Hereford in the very western part of England, basically where England meets Wales. I've got about half an hour of stuff to cover. I'm going to talk about work that I'm currently doing. It's an academic research project, but it actually was motivated by a commercial interest. And at the end, I'll talk a bit more about how I did the things that I did in terms of R packages and tools. And I'd be happy to talk about anything connected with this work, or environmental science, or R programming. I'm like a dinosaur of the R community. So we talk about that at the end. I've got about half an hour, I think, of material. It might even not be that long. And it's all pictures, I think, or mostly pictures. So I'm talking about large explosive volcanic eruptions in particular. So the point reference thickness measurements I'm talking about are measurements of the thickness of an ash deposit after a large explosive volcanic eruption. And this is the 100,000-year history of large explosive volcanic eruptions. This magnitude scale is a bit misleading. It's a log 10 scale in gigatons. So those ones that I've marked, Asso, Etislan, Toba, Ayera, and Taupo, they're hovering around or above the 8 magnitude mark. Now, 8 is 1,000 gigatons, 1,000 gigatons of ejected matter. And these eruptions are so powerful that almost all of that, well, at least half, I mean, half of it might flow across the ground as a pyroclastic density current, gets blasted into the stratosphere, and its residence time in the stratosphere, can be decades. Around 8 and above, we call these super eruptions, and they would put a dent, if they happen today, in our civilization. If you look at where modern civilization sort of dates from about 10,000 years ago, that's where my little arrow is there. So, we haven't had any of these 8s and aboves in the last 10,000 years, but they do occur. Roughly 5 of them have occurred in the last 100,000 years. This chap here, Toba in Indonesia, thought to be about 9.1. That's the largest recorded explosive eruption of all time. And if that happened today, that would probably be the end of our civilization. but anything around 8 is scary. And the one that we're looking at today is Aso4. So Aso is the name of the volcano. Aso-san is the honorific. This is known as Aso4 because it's numbered 4 in a sequence of large Aso eruptions, and it happened about, as you can see, 87,000 years ago. So what we want to know is how big was the Aso eruption? I mean, we've got a measurement here of about 7.7, but that's pretty sketchy. So we want to do a better estimate of how big was the Aso eruption. And we'd also like, because we're statisticians, to attach a measure of variability to that. Typically a 95% confidence interval is the kind of thing that my collaborators like to see. So you can see that no one's made an effort with any of these data to assess uncertainty. So we're breaking new ground here as statisticians by not only trying to estimate the size of the Aso4 eruption, but also to provide a defensible 95% confidence interval. And that's the project that we're on at the moment. It's not finished yet, but that's what we're aiming for. So this is Aso volcano taken from the air. And as you can see, it's smoking. So this is a volcano that's very much active. And you can also see that thousands of people live on the flanks of Aso volcano. And you might well ask, why on earth would anyone choose to live on the flanks of an active volcano that is capable of a super eruption? And the answer is that if you live in Japan, you don't have any choice, right? Japan is a very populous archipelago with many smoking volcanoes. So the Japanese are very aware of volcanic risk. And that's why a lot of the work on volcanic risk has been done by the Japanese. So that's Aso volcano today. These are our data. Now, each dot here is a thickness measurement. Tephra is the technical word for stuff that gets blasted out of a volcano. You can think of it as ash, basically. You can see that we have thickness measurements of Aso4 tephra on land and at sea. Now, you can identify Aso4 tephra basically by chemical fingerprinting. So if you find a layer of tephra in an archive, you can ask yourself, is this Aso? And you can usually answer yes or no. The ones on land that's from the geology. The ones on sea, those are from ocean cores. And it's hard to overstate how expensive it is to collect these data. You have to send a large ship out into the ocean. You have to drill down into the ocean bottom. You have to pull the core out. You have to lay it out on a table. You have to get postdocs and scientists to look at it, by eye, centimeter by centimeter. You have to digitize the results. You have to then take the core, freeze it, take it to Grenoble or somewhere else and store it in a warehouse. It's an insanely expensive business. So it's hard to overstate how much effort has gone into creating these data. It's already also hard to overstate, unfortunately, how inaccurate these data can be. It's the way that ash gets deposited on the bottom of the ocean is not straightforward. It doesn't just fall down from the surface. Obviously, there are currents, but there's things like clumping. So the ash tends to clump at the surface and fall as blobs, basically. So you could imagine that you could sink a borehole and you could just miss a large blob and then you'd record nothing from Aso4. But if you'd been a meter to the left or a meter to the right, you maybe have recorded 5 centimeters of Aso4. That's how inaccurate it is. So it's really hard to go from data like this with very large uncertainties to a measure of volume, but that's what we're going to try to do. But obviously the uncertainty that exists is why we're going to try really hard to get the confidence interval about right. So this is the kind of product we're looking for. This is called an isopack map. It's a contour map of ash thickness. Now, this is our current point estimate of the isopack map. It's not very good, I'll be honest with you. This is not what the geologists and volcanologists want to see. And there's reasons for that, which I will come on to. This is still a work in progress. And typically what happens is I do the best that I can with the stats that I have and the data that I have. I show it to high-powered volcanologists, and they say, yeah, that doesn't look right at all. It's just not physical for it to have that shape. You need to go back and try again. What's happened here is that the prevailing wind is from the west-southwest. So that's why the ash cloud has stretched, from the volcano, which is at 00, to the northeast. This big splurge around the volcano, which is oriented from the northwest to the southeast. That's probably not right, and that's something that we're going to try and fix in the next iteration. I sort of know why it's happened, but you show that to a volcanologist, and they don't like the look of this very much. So definitely a work in progress. But the point I want to stress for us statisticians and our users is that these data are really expensive and also really inaccurate, and that's our main challenge. So questions for us then, and to cover in this talk, how to estimate the isopac map based, so basically how to get from here to here. Is our isopac map any good? The short answer is not good enough yet, but we're working on it. And then the million-dollar question, how to provide a 95% confidence interval for total ashfall volume. That is basically how to go from one isopac map to an entire family of isopac maps, where we can use that family of distributions, if you like, to generate a 95% confidence interval for total ashfall volume. And we do have an answer to that. So we have answers to 1 and 3, and the answer to 2 is not good enough quite yet. So here's what we're going to do. We're going to do the obvious thing, and the obvious thing is to write down a basis function expansion for thickness Z as a function of location S, and as usual, this will be a linear combination of specified features. So theta j is a feature; it's a shape in the space, and the beta j are uncertain coefficients. T of S is a residual that's going to be small, and it's going to have the feature that when you integrate over Z, T is basically going to disappear. The thicknesses have to be non-negative, but they can be 0, of course. I mean, you can have a true thickness of 0, definitely as you get outside of the splashdown area of the ash. So we're not going to monkey around with logs here or anything like that. We're going to impose non-negativity on Z, but admit the possibility that it might be 0 by having features that are non-negative and imposing non-negative constraint on the coefficients as well. So that's our obvious thing. Now the question is, how do we form our basis functions? In the old days, of course, we used to use basis functions that were sort of like longitude, latitude, cos lat, longitude times latitude, and so on. That's completely gone out of the window now. It's all about localized basis functions because they give you much more flexibility. So we're going to imagine basis functions that, in our case, look like little hillocks, right? Little hillocks on the map. And the way to create a little hillock is with, well, I like to use a bi-square function. That's basically a bell-shaped function that sits on the unit disk in 2 dimensions. So think of a little bell on the unit disk in 2 dimensions. Now, we want lots of them, which means we want a variety of shapes and locations and sizes. So then what we do is we take our little bell-shaped function on the unit disk. So down here, think of x and y as being the set of points in the unit disk. First of all, we're going to expand the x and the y values. So we're going to go to ax and by. So that's going to create basically an ellipse instead of a circle. And that ellipse is either going to be lying down or standing up. And then we're going to rotate that ellipse, right, through an angle theta to give it some tilt. And then we're going to push that tilted ellipse over to some other location, x0, y0. So we can start with an individual unit disk, and we can map it to hundreds or thousands of different ellipses. And each ellipse is the basis, or is the base of a bi-squared function, which looks like a bell-shaped hill. So that's going to be the way that we construct our response surface for thickness. We're going to use hundreds and hundreds of bell-shaped basis functions where the bases of the bell shapes are ellipses. Now, we've got all these bell-shaped functions. How do we scatter them around the domain where the measurements have been taken? Well, the obvious thing we want to do is we want to have more bell-shaped functions, more basis functions in regions where we have high density, because that gives us more flexibility where we have more data. So the tempting thing to do, and this is not a crazy thing to do, and splines, for example, often do this, is put your basis functions at the sites where you've made the measurements. But this definitely leads to overfitting because the sites are very, some of them are very far away from others. So basically you just fit to the site itself and you don't do any extrapolation into the big space between sites, which is not great. And yet we do want to have more basis functions where we have more density of sites. So what I ended up doing, and I think this is a good idea, is I used the Delaunay triangulation of the sites to create, if you like, a space-filling set of centers for the ellipses. And in particular, what I did is I created the Delaunay tiles of the sites, and then I ditched the really small ones, and then I put a center for my basis functions in the centroid of each remaining tile. So this is what that looks like. The black dots, as you can see, are actually where we've made measurements. So the black dots are the sites themselves. The Delaunay triangulation is the triangulation that you get by associating every point in the map to its nearest site. So, you get these triangles, hexagons, whatever they might be. I mean, you get shapes, but you triangulate them. And then you get lots and lots of triangles where, so down here, for example, in the southwest, there would be lots of tiny triangles there. And then I just deleted the really small triangles. And I also deleted the ones that lay outside the convex hull of the sites. Right? And then I kept the rest. And I ended up with 71 centers sort of scattered over my domain here. And as you can see, this has achieved the aim I wanted of making sure that we have high density of centers in regions where we have high density of sites. Yeah, but we get low density of centers out here, for example. So that was my idea for just creating a sort of space-filling design that sort of reflected the density of the sites without actually putting a point on each site. And we have 100, literally exactly 100 sites, and we've ended up with 71 basis function centers, right? So each red circle is a center. Now, the next thing we do is we put more than one ellipse on each center. In this iteration of the study, I've put 10 ellipses on each center. I've got, if you look at the top row, big ellipses, and at the bottom row, small ellipses. So these chaps on the bottom row are half the area of these chaps on the top row. So we call that a multi-resolution approach. Right? We've got basis functions with 2 different length scales. And then for each size, I've got like the circular ellipse, right? It's actually a circle. And I've got the lying down ellipse. And then I've got the leaning to the right ellipse. And I've got the standing up ellipse. And I've got the leaning to the left ellipse. Okay, so I'm going to put 10 of those 10 ellipses at every center. And since I've got 71 centers, I've got 710 basis functions altogether, just sitting there waiting to be used in my response surface for thickness. Now, if you've got 710 basis functions and only 100 very imprecise measurements, then clearly something's got to give. So the way that we fit this is with an L1 penalty that basically squeezes unwanted basis functions out of the fit. There's a very efficient way for fitting an L1 penalty called the lasso, which some of you may have heard of. It depends upon a penalty coefficient lambda, which can be learned by cross-validation. And what I've done here is a double cross-validation. So I've chosen a range of different areas for the ellipses. And for each one, I've chosen a range of different coefficients for the L1 fit. And we're looking for the minimum mean squared error by cross-validation. And this chap down here, which is a 2 million square kilometer basis function, that's the bigger basis function, which turns out to have a lambda of about 0.15 or something. This is a log scale down here. Yep. This is the chap that we go for. Okay, so I'm going to use basis functions with areas of 2 million square kilometers, and there's the bigger ones, and 1 million square kilometers for the smaller ones. That's my resolution, multi-resolution approach. So if I just go back here, so I'm going to use 2 million square kilometers for these chaps and 1 million square kilometers for these ones. So what happens next? Well, we let that rip, basically. We let the fitting happen. We learn the bandwidth and the sparsity coefficient by cross-validation. And that gives us a subset of the basis functions that are selected for the model, okay? And this is a map of which subset was selected. you don't get an awful lot from this map. I mean, I like to look at it anyhow, but it doesn't tell us a lot about the resulting fit, because these are just the bases of the basis functions, but the height of them is controlled by the coefficients, the beta j's. So you can't really see what's going on, but it's still fun to have a look at this map. Because these are all, these have compact support. So, it's zero outside of the envelope of all of these ellipses here. So we know that that's going to be the extreme end of the contour. And then you do the fitting, you estimate the betas, you get beta hats. Then you basically predict the response surface on a high resolution grid, so that you can draw a contour diagram, and that's how we get our isopac map. Okay, so there's a lot going on there. We have the 710 basis functions. We used an L1 penalty to be able to fit a subset of those. We selected a subset, we fitted their coefficients, we did some cross-validation for the smoothness and so on, and this is the result. And yes, this is the picture that the volcanologists and the geologists say is not realistic enough yet. So more work needs to be done there. And I think that the solution will be, I just go up, I think we probably need 3 sets of resolutions. So we can have like large, medium, and small. And I'm not too worried about small, because small can lead to overfitting. If you were to dump a small basis function on a site, it would just overfit that site. But because I pushed the centers away from the sites, I'm not too worried. So I think that if you look at this picture again, I think part of the reason that we've got this big splurge here, which is the wrong shape, is this is a large measurement that is out on a bit of a limb, but it sort of wants to fit into the ellipses that go like this. So I think if we went for another resolution to allow for a smaller fit in here, maybe we would lose this feature of going southeast to northwest. Right, so next steps. We need to turn the fitted model into an estimate for tephra 4 volume. Basically, we need to integrate over the response surface. And then we need to wedge this entire process into a bootstrap, which is the way that I'm going to compute a 95% confidence interval for volume. Now, part 1 is easy, okay? All we're going to do is we're going to dump an integration grid onto our map. I'm integrating in polar coordinates just because it's more fun. So I just colored these in alternate rings. So the color doesn't mean anything, it's just so you can see the structure. So this is like a midpoint rule basically, but in polar coordinates. And that allows us to turn any response surface into a point estimate for volume. If you think about how this works, when you do a numerical integration with a response surface, the result that you get is actually a linear function of the coefficients, because the integration points are values of S, and they go inside the basis functions, and the betas stay outside. So it's important to remember that a numerical integration like this is a linear function of the beta coefficients. Now, the bootstrap itself, let's be honest, statisticians have strong opinions about the bootstrap. I'm not, I have to say, a big fan of many forms of bootstrap, and there are many forms, but the one I can tolerate is the studentized pivotal bootstrap. It seems to work quite well for me, I have to say, and there's lots of reason to think that of the various types of bootstrap that you can get, ranging from the quantile bootstrap, which is a bit of a shocker, up to the studentized pivotal bootstrap. The studentized pivotal bootstrap is not too bad. Okay, but it's basically, if you're not familiar with the bootstrap, it's a numerically very intensive procedure for turning an algorithm into a confidence interval. So I've got an algorithm for generating volume from a data set, and I'm now going to apply the bootstrap to that algorithm to compute a confidence interval. Now, the studentized pivotal bootstrap requires not just a point estimate of the volume, but it also requires a standard error for the volume estimator. And this would be hard in general, but in our case, we can make a shocking approximation, which I definitely wouldn't want to defend in court, where we can just pretend basically that we fitted an OLS model and the betas that have been zeroed by the L1 penalty were never there in the first place. Right? I'm confessing to you, but that's exactly what I did. And then we remember that the estimated volume is a linear function of the betas, and that allows us to generate a standard error for the volume. So we can actually do the studentized pivotal bootstrap here, because we can get a sort of an approximation to the standard error of the volume estimator. And then we use semi-parametric resampling of the data set. You fit the model, and then you permute that, then you resample from the residuals and reconstruct the observations that way. That's fairly standard. Now, how do we know that the bootstrap is working? Well, that's always a good question in practice. The clue is in the name. It's called a studentized pivotal bootstrap, and there is a sense in which, if all the asymptotics are working appropriately, and that's a big if, remember, the asymptotics involve also the number of observations, and I've only got 100. But if they're all working appropriately, then the pivotal statistic should be approximately a student t or a normal. So that's a statement about what the pivotal statistic is. But the key thing is this picture here. This is a not shocking picture that suggests that the bootstrap is sort of behaving. I mean, I'm not going to put any money on it, but it's doing a fairly good job. And the point about a picture like this is, so we're looking at this pivotal distribution. It does look kind of T, so that's okay. The point about a picture like this is that when you've done this 100 times with 100 different approaches for trying to generate a volume, and 99 of the times this pivotal value looks absolutely shocking, and you know you've done something wrong. So when you see something like this, right, the power of this diagnostic is really quite high, because if the studentized pivotal bootstrap isn't working, this looks really bad. So this is not too bad, I would say, and I'm hoping that when I go to higher resolution with my third set of ellipses, this retains that fairly attractive sort of student T shape. Anyhow, we turn the handle. My laptop heats up because I'm doing everything with multiple cores. I'll talk about that in a second. And we do generate a 95% confidence interval for tephra full volume. It's 190 to 430 cubic kilometers. Now, when a volcano has a massive explosive eruption, roughly half of the stuff gets blasted into the high atmosphere and then settles out on land and sea. That's the tephra full volume. And roughly half of it goes up in a cloud and then comes down under gravity and flows over the landscape. That's a pyroclastic density current. Those are the things that travel very fast. If you can see one, it's already too late because it's traveling much faster than you can respond. They're so powerful they can flow over mountains, and with a super eruption, I mean Toba, for example, Toba covered the whole of the Indian continent with ash, but I don't know how long the run out was for the pyroclastic density current, but it was probably thousands of kilometers. So roughly speaking, rule of thumb, you get half the mass in the PDC and half the mass in the tephra full. So if we actually double our confidence interval for tephra full and call that roughly total ejected mass, and then convert that onto the magnitude scale, we get 7.5 to 7.9 for the ASO4 eruption, not quite a super eruption. But you will notice that the uncertainty is very large, and that's entirely appropriate. It's very, very hard to understand how big an eruption that happened 87,000 years ago actually was. So 380 to 860, it might seem like a big interval, but it's entirely justified. That's the kind of thing that you would show a volcanologist, and they would say, I'm not at all surprised. In fact, it could even be bigger. So that's where we are at the moment with this work. The latest iteration is not ready for publication because the volcanologists don't like the shape of my ISOPAC map, but we're doing another iteration next week, and with any luck, we'll be there. Now, I want to say just in the last few minutes a little bit about the computing and the R packages. So I did this on a very new Dell XPS 13 Intel 5 laptop, which I bought in February. And it was a bit nerve-wracking because I bought it, it came with Windows on it. I immediately erased Windows and put Linux Ubuntu 20.04 onto it. So I only use Unix, Linux in particular. It's a nerve-wracking moment to take £1,000 computer and simply destroy the operating system in order to put on a new operating system which might not fit. And there was a bit of fiddling around to do in the BIOS, which made me very nervous, but in fact, it has a happy ending. So this laptop is now happily running, this brand new Dell laptop is happily running Linux Ubuntu 20.04, and it's running it very fast. So I'm definitely happy about that, but it's a nerve-wracking moment, and I don't recommend it if you're worried about bricking your brand new laptop, because that would be a bad thing. This is the Rougier workstation. I'm sure your workstation looks very similar. Key features, of course, the massive pile of papers on the left-hand side, which when it topples off, then you know it's time to file those papers. The full waste paper basket, and of course, the combo mouse mat and jotter pad. I'm sure we've all got one of those. Now, as for packages, so first of all, I strongly prefer data table to using data frames or to using the tools in the tidyverse. I find data table is very powerful. It's basically an entire SQL database inside the square bracket operator. It's got a shallow, then steep, then steeper learning curve. So shallow, you can just replace data frame with data table and things become easier. To use the SQL type facilities and to work efficiently with massive data sets requires quite a steep learning curve. I'd be honest with you, I can do some things with data table just off the top of my head. Mostly I have to look at the cheat sheet or go back to a previous piece of code where I did the thing that I want to do again and figure out how to do it, but I strongly prefer it. I get data out of spreadsheets using read_excel, and I occasionally pipe using the Magritte pipe operator. They're both from the tidyverse. I don't like data in spreadsheets, but all of my science collaborators do. So you just have to live with that. You can get data out of an individual tab using read_excel, which is very useful. But I have to badger my collaborators to put their data into spreadsheets in such a way that I can read it out automatically. So there's usually a few iterations on the spreadsheet itself. And in one other project that we worked on, I basically spent a year with the scientists constructing a spreadsheet that was state of the art for data extraction using these kinds of tools. And it was a big job, but we got there in the end. So in that case, the spreadsheet became basically an entire SQL package, and each tab became a table, and tables were linked. Cases were linked by common keys across tables, but you have to do a lot of work with your collaborators because they don't necessarily understand that foo with a small f and foo with a big F look like different variables to you. And long variable names with spaces are not necessarily very useful. So you do a lot of work with your collaborators to get to the point where your spreadsheet is ready for simple extraction. I drew my maps by hand. I didn't use ggplot2, so I just like using the polygon function. So I'm very old school, as you can see, but the ggplot2 map data function is great for getting data out of the maps package into polygons, and then I can just dump the polygons down onto the page using the polygon function. I like transparent colors. I just think they present better, but also, of course, for overplotting, they're brilliant. And then I use the scales alpha function for that. So that's the alpha function in the scales package. So my maps, for example, were drawn by me using polygons. They weren't drawn using ggplot2 or anything else. The triangulation and clipping for the centers was done using deldir and polyclip. They seem to work really well. The lasso for the L1 fitting was by glmnet. Because I'm using basis functions with compact supports, there's lots of zeros in the model matrix, and glmnet fully recognizes that you can use big M matrix package for sparse model matrices, and that's very efficient, both in terms of storage and in terms of speed. glmnet is a great package. It allows you to impose, for example, non-negativity constraints on the coefficients. So you can fit with non-negative coefficients automatically, which is great. It's a very powerful package, actually. I have to say I use it for lots of different things. And then for the Bootstrap, which is an easy to parallelize operation, I use doMC and for each to do the Bootstrap. I could just have used MCLapply, multi-core lapply, but I've come round to the idea of using do MC and for each instead. I think that they're a bit clearer to use. I'm not sure they're quite as fast. With the Bootstrap, it's really important to control the random number seed. So that's why I used for each rather than like a more simple repeat, so that I get full reproducibility for all of my calculations. Okay, I think that's it. So I'm very happy to take questions, and I'll maybe hand back to Kevin to do the next stage.
Hi, folks. Yes, if you want to ask questions, just put them in the chat there. But just to sort of start off, actually, sort of not a question really, more of a sort of comment. Just a sort of a remark that you have previously won the Barnett Award from the Royal Statistical Society very recently.
Mm-hmm.
I'll just read out the citation for that. It's on the Royal Statistical Society website. The Barnett Award is made to Jonty Rougier for his internationally recognized contribution in the field of environmental statistics, risk, and uncertainty quantification. Rougier's work is motivated by a strong philosophy of supporting the applications of good statistical practice in the environmental sciences. There's a couple of more things there to say, but that's the main part of it there. Just first off, congratulations on that.
Thank you.
A lot of people actually will be watching this series of videos and they would not be familiar with the subject of environmental. Let's say there are data science students or machine learning students, and they're very young in their careers and so on, and they would not be familiar with the whole subject of environmental statistics at all. So just to first off, just sort of like a bit of a background to that, a broad picture of what environmental statistics is. Now, I know that's a big question, but
it is a big question, but the thing that I will pull out about doing environmental statistics is you're always working as part of a team. It's really not the kind of thing where you find a data set online and you go into your study and you analyze it and something cool happens. The data themselves they're usually really complex, and it takes a specialist to understand them. The data sets can either be really small, like some of our volcanology data sets, or really big. So another project we're doing at the moment is we're trying to unify massive remote sensing data sets with GPS data sets over the whole world to figure out how much water there is and where it is. Is it on land? Is it in the oceans, and so on? So you go all the way from trying to squeeze as much information as possible out of 100 measurements, which is what I'm doing right here, to trying to find a way to do anything at all with a terabyte of data, which is what we're also doing at the other end of the scale. And you can't do either of those two things without really a strong team of people who are all pulling together. You definitely need the science expertise to manage either of those two extremes, and presumably all of the area in the middle as well. So I've always worked in environmental science as part of a team. I've been the statistician or one of the statisticians, and there's usually been several specialists. So with my volcanoes work, for example, I've worked closely with Steve Sparks and Kathy Cashman at the University of Bristol for over a decade now. And although some of the products, they seem statistical, they don't exist at all, except for the input of Steve and Kathy, because so much domain knowledge is required. And I'd say that was a defining feature of environmental stats. It's not like one person in a broom cupboard. It's statistician as part of a team of specialists.
Okay, good stuff. The next question is really, first off, actually, just a sort of more practical question. Very recently, there has been an eruption in St. Vincent and the Grenadines, and also previously, about 10 years ago, there was a very serious eruption in Montserrat, and also a couple of the Icelandic ones have made the news. What sort of insights can this sort of as kind of statistician bring to what's going on? Is it possible, really?
Yeah, I mean, so obviously, I mean, the people that I work with are heavily involved in the current situation in the Caribbean. I'm not involved personally, although I'm going to get to look at the data next week because there's a very rich data set coming out of this. There are really two things that you can do as a practicing statistician in this area. I mean, one is you can help with the planning, and I mainly do that. So the question is, how often do we expect? an eruption of this magnitude to occur, what do we expect the harm to be? Should we be planning a mitigation strategy, or is this so rare that in fact we should be spending our money elsewhere? Those are planning questions. And predicting what we call the exceedance probability curve for a volcano or for a volcanic system, that's something that you do, at the planning stage. The other thing that you do, which I think is less recognized, is that we are really good as statisticians in thinking about uncertainty, and we should be specializing where we can in decision support in situations of high uncertainty. So statisticians who have worked in decision theory, statisticians who have the clarity to understand how to improve decision making under extreme uncertainty, that's really valuable while an emergency is actually happening. And it's not just asking the right questions and attaining clarity. It's also things like understanding how to get the best out of your experts. So, one of the things that we understand as statisticians and as psychologists is that you can't just get people to tell you stuff, right? There's this elicitation method called BOGSAT, BOGSAT, bunch of guys sitting around a table. It's terrible at finding out stuff, but so often the emergency happens, the COBRA meeting is called, there's a bunch of guys sitting around a table, and a bad outcome will sometimes arise. And that's because there's lots of individual and group reasons why people are unable to reflect their true judgments in that situation. So one of the things that a statistician can do, as well as bringing in uncertainty of the theory and practice of decision making under uncertainty, is they can be in the room as a facilitator and they can say no to BOGSAT, right? They can do things to help people to make better assessments of their own uncertainty. And there's tons of things that you can do along those lines. There's a good book by Tony O'Hagan and colleagues, 2006, called Expert Judgment. And there are a few others too. There are experts like Roger Cook in this area. But the entry level is not complicated. There are things that you can do to say no to BOGSAT that won't necessarily have occurred to your experts because they're panicking about all sorts of things, but you can really help them there by being in the room and making the elicitation process a more effective and less stressful process for the people involved.
Good stuff. Just actually sort of just to sort of switch over, you published a book with your colleagues, I believe you just mentioned there, Sparks and Hill, Risk and Uncertainty Assessment for Natural Hazards. So would it be fair to say that a lot of the work that you do is sort of applies to other things other than volcanoes, for example, wildfires or earthquakes or something like that?
Yes. So, the hazards that I've worked on directly are obviously volcanoes, floods, avalanches and landslides, and then hydrometeorological hazards connected with climate. They seem to me as a statistician to have many of the same features, but of course, when you get into it, and you'll discover that the language used by one set of hazard experts is not the same as another. So you can't just wade into a field and expect to understand everything that's happening because of the commonality of uncertainty and statistics. You have to get tooled up. But by and large, the problems are basically the same. As I said before, you either have like very sparse, bad data, like I have here, or like we have with avalanches. People don't spend a lot of time in the paths of avalanches collecting data for very good reasons, but you still need to understand about avalanche risk. So, so in those kinds of situations, there's a lot of stats involved. But yeah, I would go back and say an area where I haven't worked very much is seismology. And I've looked at seismology and I found that frustrating because I haven't been able to understand the thought processes of the seismologists to a sufficient degree that I can map them onto my own concepts of uncertainty. So you'd think that the same concepts would apply across all of natural hazards, but in fact, in practice, there are sort of barriers to entry that you have to overcome.
Good stuff. Just actually, I noticed on your website, I just have your website open here. Risk assessment for low probability, high impact events. small, complicated data. And I believe that's really what you just covered there. Just for the point of view of somebody who's sort of interested in that sort of stuff, are you talking about extreme value theory or probability distributions that would not be commonly encountered on undergraduate courses? Or let's say I was interested in finding out about more about that.
So I don't use extreme value theory at all in my own work, because I don't feel that the kinds of applications where I work are conformable with the underlying requirements of EVT as an application. But what I do like is the generalized Pareto distribution, which is a distribution that occurs when you do extreme value theory as peaks over threshold. So there's a theorem that says that under certain conditions, the tail of your peaks over threshold analysis of extremes. So peaks over threshold is, you've got daily, say, measurements of some quantity, and you draw a line at 4, meters per second or whatever it might be, and then you only keep the data that lies above that line, and in the limit, you can show that data will conform, that tail will conform to a generalized Pareto distribution. Now, I don't use the generalized Pareto distribution for that reason, but I do like it as a distribution. It's got 2 parameters, and it's got a very long right-hand tail in the situation where it's unbounded above. It has a version where it's bounded above, which is also useful. But I like the long right-hand tail because many of the hazards I look at vary in size over several orders of magnitude. So a volcanic eruption, for example, 0.1 of a gigaton is already considered to be a big eruption. Yep. 1,000 gigatons or 10,000 gigatons can happen. So we do genuinely cover 6 orders of magnitude in the size of a volcanic eruption. And there aren't many distributions that are really comfortable with that kind of long tail. So I like the generalized Pareto for those kinds of situations, especially when you're dealing with a phenomenon which can have a size measurement that varies by many orders of magnitude.
Good stuff. Just a sec, I'm just still on your website. You mentioned that you're also interested in spatial statistics at global scale, big complicated data. So just actually what we talked about there, climate change data.
So the work that we're doing at the moment on that is it's basically led by Andrew Zammit-Manjan, who's at Wollongong in Australia, working in the same group as Noel Cressy. We're looking at reconstructing, for example, very high resolution global data sets like sea surface temperature. And if you fly a satellite around the world to collect these data, of course, it doesn't get to see through clouds or ash or sand, for example. So you get very high resolution in some places, but you get quite a lot of dropout, either pixel by pixel or over larger regions. And these data are very complex because not only are there a lot of them, but they're not traditional spatial data, they're not stationary, they're not isotropic. They've got lovely structure, but it's not the kind of structure that you can capture in an old-fashioned way. So Andrew and I have been working in particular on how to model these data to allow for all the flexibility that we require to capture the local features, but on the kind of scale where we can literally put in millions of observations and do a reconstruction. And that again is incredibly computer intensive. Andrew has a much bigger computer than I do. And we spend a lot of time figuring out how we can take MCMC schemes and run them using multiple cores. MCMC is inherently quite serial. You draw a proposal, you either use it or you throw it away, and then you do it again and again and again. But drawing a proposal itself can be over a huge distribution, and we spend a lot of time figuring out how we can parallelize that, either exactly or approximately, so that we can do MCMC at scale on a 48 core machine, for example.
Good stuff. I think it's commonly known that your climate change is a subject very close to your heart. Where would that sort of subject area be right now in terms of statistics and environmental sciences or sciences? For example, if a young data scientist wanted to do something more in that area, what could they do?
That's a really good question. To be honest, I'm a little bit behind the curve on climate because I haven't worked in it actively for several years now.
Mm.
The kinds of things that I think would be interesting for data scientists who were comfortable with things like neural networks or Gaussian process emulators, things like that. The area that I think is interesting is in downscaling or subgrid scale processes. So this is where you build your climate simulator and you haven't got all the time in the world, and so you can't push the resolution too high because it would take your simulator too long to solve. I mean, basically, if you want to run a climate simulator, you have to start it in about 1700 and run it through to 2100, I think, basically, to do one run. So you've got 400 years worth of run. Now, these simulators, they run very slowly, even at their top resolutions. They tend to run at about 100 model years per calendar month. So you're talking about 4 calendar months for one run. And the question is, could we speed that process up by going to lower resolution? If you go to lower resolution, obviously the computer runs faster. Remember, resolution scales, or rather compute time scales, like the 4th power, because you're dealing with cubes in time. So, you can shrink the resolution a bit and make your grid cells a bit bigger effectively, and you can get a massive speed up. But of course, you also lose things. And in an ocean model, what you lose is mixing through vertical mixing through turbulence, which is there in the underlying equations. It's in the Navier-Stokes equations, and it would be there if your resolution was 1 meter squared or 1 meter cubed for your solver, but it's not there at 100 kilometers. So you have to put the vertical mixing back in, basically. And I think one of the really interesting areas to look at is whether we can take massive amounts of computer simulated data at, say, 2 different resolutions, and we can figure out how to model the effect of mixing, right? In the high resolution simulator, but only using the data from the low resolution simulator. So that's a very complex prediction problem. It doesn't feel like the kind of problem that you would be able to solve with basis functions, but you might be able to solve it with a massive neural net. And then what you would do in practice is you train your neural net offline, and that would be very expensive. And then you'd run your low resolution simulator, but you'd put the vertical mixing back in with your neural net.
So, sorry, just actually somebody's joined another question on the chat. My YouTube one, if there is a knowledge telling you the correct shape, why are you not introducing that knowledge in the modeling instead of tweaking until preconceptions are satisfied?
Yeah, that's a really good question, and it's one that we're struggling with as well. The thing is that our aim here is to produce a 95% confidence interval. That's the thing I care more about than the ISOPAC map. But the ISOPAC map has to satisfy the volcanologists, obviously. Now, the thing is that we know how to turn an algorithm into a confidence interval using the Bootstrap. Yep. But it only works for an algorithm. That is, it only works for a definite function that sees the data and spits something out. And the problem is that you want your algorithm to work not just in the case of ASO4, but also in the case of Toba, right? Or any other volcano that you might study or related problems. So you've got to be careful about really tuning the algorithm to be specific to ASO4, because then you lose the ability to create confidence intervals more generally. So I'm looking basically to find a sufficiently flexible statistical framework that my volcanologist colleagues are satisfied captures the inherent physics of the problem, the effect of the prevailing winds, the thinning in the upwind area, those kinds of things. I believe that it ought to be possible to get to that with a sufficiently flexible statistical arrangement. I don't want to inject too much ASO4 knowledge into my algorithm, because then it doesn't become usable elsewhere.
Good stuff. A second question from the same attendee, my YouTube one. Could you explain your strong feelings against bootstrapping? Would it not be sage to assess the robustness of your ISOPACs by successively ignoring one observation point?
So the observations are really sparse. I think, I mean, one of the problems that we have actually, I mean, this is slightly tangential, but I'll come back to your question in a second. So the problem that we have is that we've got these massive empty areas here, and no one has taken a core in these areas. So we just don't know what's here, and we don't know what's here. So we know that uncertainty is going to be absolutely massive. It's not even obvious that we're capturing that uncertainty with a confidence interval, because the confidence interval is predicated on the locations that we have. If we were to leave an observation out or put one in, it's not clear to me that we would really be getting to the heart of the matter. And cross-validation itself is a very complicated thing. I think if you look in, I think it's Elements of Statistical Learning, Chapter 8, there's a good discussion, or maybe it's in F1's book, Computer-Age Statistical Inference. There's a good discussion, I think it's that one actually, Cassie, of what cross-validation is really targeting, and it's not obvious that it's targeting the thing that you want it to. On the subject of the Bootstrap, the one that I don't like, and I'm not alone in this, is the quantile bootstrap. I think, as Peter Hall described it, looking up the wrong number backwards in the table, it's very difficult to understand the philosophy behind the quantile bootstrap. And there are various more or less ad hoc corrections to get higher order accuracy in the coverage of your confidence intervals, which I can sort of see, I can do the maths, but they don't really speak to me. The studentized bootstrap, on the other hand, I really get. It fits in with my understanding of asymptotic statistics, and I can sort of, the validation I can do through looking at the distribution of the pivotal statistic is quite convincing to me. So I like it, but it does impose a higher cost. The quantile bootstrap just requires you to be able to generate an estimate. Yeah. The studentized pivotal bootstrap requires you to generate an estimate and a standard error. So it's a bigger ask, but I think if you can meet that ask, it's a much more reliable bootstrap platform than, say, the quantile bootstrap.
Good stuff. So that's it. We're up to date on the questions on the chat. Just regarding environmental statistics, is sort of very at a practical level. It's for a lot of people, it'd be environmetrics, for example, water quality and stuff like that.
Mm-hmm.
Just and I feel that that's very fertile ground for a career young data scientist who wants to sort of get into that field. The data sets available for water quality and so on, or flood risk, or water meters and so on. Just actually, would you give any advice to somebody who's interested in a data science career but wants to bring it, have a natural science component to it?
It's a good question. I think probably flooding, hydrology is the area to go to. Of all the areas in natural hazards, which I know well, it's the one that's most tooled up with uncertainty. They would be using extreme value theory in that area, except for the fact, of course, that the boundary conditions are non-stationary because of climate change. So it's a bit tougher. But there's lots of fun stuff. I mean, Adam Butler at BIOS in Edinburgh has been doing some really great work on networks, flows on networks. I think Jonathan Torner's worked in that area too. And that seems like an area that would be very interesting to get into more. So it's not just about what's happening at this river, but it's thinking about the network of channels upstream of the point that you care about, and how, how the landscape releases water into the channels, and how the water flows down the channels at different speeds and so on, and how they end up combining at your location of interest, which might be the center of Carlisle, for example. That's a really interesting problem, because it's got a spatial element, it's got a computational element. There are graphs, which we always like as mathematicians. It's a really interesting problem, and an important one too. Will Carlisle flood? And maybe more to the point, how will it flood? I think that's a really interesting question to answer, because of course, how will it flood determines how the flood itself translates into harm, and it's harm that we care about when we think about natural hazards. It's the harm, it's the damage they do to humans and non-human animals, and infrastructure and so on, that we care about. So you can imagine there are some floods which they might cause the water to rise in the middle of the city, and they might flood a car park, but it's not the end of the world. But there are other floods that might cut like a main road, or remove access to emergency services like fire stations and hospitals. So how does the flood occur? You know, what roads get cut off and in what order? I think that's a really interesting problem. And I think that's the kind of problem where a tooled up data scientist could do something great. I mean, on that topic, actually, just for 1 minute comment, is that there is some interest building, I think, in using agent-based models for how people and drivers respond to an emergency onset. You know, so that's like a fun thing, and data scientists would be all over that. So you know, you imagine you fill Carlisle with agents operating under quite simple rules, and then you gradually flood Carlisle according to one particular flood pattern, and you see how the agents respond. You see, you know, did they get across this road before it floods, for example? That would be a lot of fun. Agent-based modeling for responses to flooding, I think, would be a good thing for data scientists to look at.
Great stuff. So just actually, you mentioned GLMNet, do MC, and a couple of R packages there that pertain specifically to the work here. And you know, they're well worth having a look at. Just beyond that, they just other sort of R packages that you might sort of like recommend having a look at, or
yeah, I use a lot. There's other ones I use more that I haven't listed here.
are any favorites even that you just?
Yeah, no, I think these are my main ones, actually.
Yeah, okay.
I would draw your attention to the matrix package for sparse model matrices.
Yeah,
yeah. Those of us who work with very large objects, we often find ways, principal ways if we can, but unprincipled ones if we can't, to sparsify our massive objects and then to hold them using. So there's big M matrix and there's SPAM, two different packages for sparse matrices. And that's definitely a nice thing about GLMNet, is it understands the big M matrix package. I think I do a lot of in R, which maybe people don't, is I do create a lot of S3 objects. When I'm working with something, I tend to make it into an S3 object. So for example, I've got a sort of like a list of ellipses object to do this work here. And then I overload the operators so I can like use the length operator on it, for example. I can use the extraction operator to take out a subset of the ellipses, things like that. So that may be worth looking into. It's not a package, but it is something I found really helpful, is if possible, try and containerize the objects that you make in R using S3 classes, and then overload simple operations like length, for example, to make your code much cleaner.
Good stuff. I believe that you have a very long-standing relationship with R, going back to the 90s. Just tell us about that. We'll sort of wrap it up soon, but actually that's a very interesting subject about R version 1. Yeah,
so I became an R user when it was still in the 0 point somethings, and at that stage, I mean, R was already great, and I think we must be talking here about 1996. I think even then we were thinking about using it for teaching. I don't think we quite got there yet. I think we were still using S+ for teaching, but we were thinking about using it for teaching. This was at Durham, and there were several of us in the group who were keen R users. And at that stage, I mean, there were bits of R that worked really well, and there were bits of R that didn't work really well. And the hands-on R people, of who I was one at that time, would change our core code to make it do the things that they wanted to do better. So for example, early on I was doing a lot of work on variances of matrices. And if you think about the variance of a matrix, it's a 4-dimensional object basically. So I needed a lot of high dimensional operations, including I needed to be able to permute matrices to move, to swap the order of the rows and columns and the third and fourth extents. And the array function, so the aperm function, was running very slowly in R. It was written in R actually. So I rewrote that in C using the Python concept of strides, and then that became that went into the core R core as the rewritten array function. And I think a lot of people did things like that at the time where things weren't running very fast, or you wanted functionality that wasn't really there. I wanted to use outer products a lot, so I rewrote the outer function. I wanted to use Kronecker products, so I provided a Kronecker function, and I overloaded the %x% as the Kronecker operator. I wanted to use sprintf, so I wrote an sprintf function that wasn't very good. It did the trick, but it came back with bad error messages. And then Brian Ripley, who is brilliant, tidied that up and made it run a lot better. So I think at the time, that's sort of the way the things were happening. People were finding things about R that weren't quite what they wanted, and they were rewriting the R functions or writing C underlying functions to make it all work.
Good stuff. I believe you were in Vienna for the grand opening.
Yes, I was. I mean, there was a meeting, I guess it was 1997, but I couldn't be absolutely sure.
Okay.
When R went to version 1.0. That basically happened in a meeting in Vienna, where I was fortunate enough to be present, and I met, face to face, a lot of the R people who were involved at the early stages then.
Good stuff. So we've covered a lot of ground there in the Q&A. Just one last question, actually, about the COVID crisis. So this interview is taking place in late April 2021, and both the Ireland and the UK are still in the midst of the COVID crisis. Just a bit of context for anybody watching this in the future. So just how has it been for you? How's it affected your career and your workflow, and both as a statistician and as an R user?
Well, it's a thing, isn't it, about COVID, is that the temptation is to get involved. I've resisted that temptation, to be honest. So I've continued doing the stuff that I was doing before, working with clients and developing my own portfolio of research interests. And I've tried not to get involved with, I have got involved in a few different things with COVID projects, because I don't know, it just seemed like there were a lot of people involved already, and I didn't really feel that I had anything to add. But the one thing I would come back to about the COVID crisis, I'm speaking as an outsider now, because although I've done one or two bits and bobs, I haven't done anything serious. The one thing I would reflect on is what I said earlier. If there's been one thing that I think's been missing from the response to the crisis, it's been an understanding of how people do and should, present their judgments about very uncertain things. There hasn't been enough basic decision theory. What do we need to solve this problem? What does a successful outcome look like? What are our main actions? And there hasn't been enough structured expert judgment. There's been too much bogsat, too many bunch of guys sitting around a table. And I think not nearly enough structured elicitation designed to extract the best possible understanding of a problem from a group of people and to turn that into actions. So, that's my view as an outsider. It's not a view that I hold alone. I think many people who work in the area of decision support and making choices under uncertainty feel that there's been a missed opportunity here for us to use what we understand about the psychology of humans in the presence of uncertainty and in groups to have done a better job than we actually did in terms of getting information from Sage into Cobra and so on. So that's the only reflection I have on COVID. I think it's maybe a missed opportunity there.
Good stuff. I think we better wrap up the Q&A because we've actually done a really good run at it. So I'd like to thank you for joining us, and you've been on my wish list for ages to have you on this, and it's great that you've joined us, and I really appreciate it. Folks, we're going to wrap it up now. We're not having a webinar next week because it's essentially exam time and all that. Basically, people want to be out in the sun. We'd just like to thank our sponsors, Jumping Rivers, and who have been, as I sort of said at the start, being great supporters of the R community over the last few years. And so we'll announce in our next webinar very soon. But we leave it there, and just actually sort of remember the word of the day, bogsat, which is going to sort of stay with me now for a while. Actually, bogsat, yeah.
No to bogsat. No to bogsat is our message.
No to bogsat, exactly. Yeah. Sort of, it's firmly against bogsat. Okay, folks, we leave it there. Thank you very much, and see you soon. Now we're offline.
Thanks, Kevin. That was really